So normally in class, I would draw this whole process out with you guys several times, but unfortunately we can't do that. If you are a visual learner, I would recommend drawing this out yourself at home, but we're going to go through the stimulation of a neuron and a muscle fiber together. So this is our neuron, here's our cell body, axon, telodendria with our axon terminals, and this is our synaptic cleft here, we're going to imagine. I had to kind of twist it to get everything to fit. And then here down is our muscle fiber. So this is our sarcolemma, then our T-tubules come down, continuous with the sarcolemma, and then on either side of the T-tubules, this is our sarcoplasmic reticulum. And then down here in black is our myosin with our myosin heads. This orange line is our actin, troponin is in green, and then the tropomyosin in red. And right now at rest, troponin and tropomyosin are bound and covering the active sites on actin. So at rest, we would have sodium would be outside of our cell. We're going to have some sodium out here too. Potassium would be inside. And then calcium, we're going to have calcium extracellularly. And then we're going to have calcium inside the sarcoplasmic reticulum because it's the storage site for calcium within our muscle fiber. We also have acetylcholine stored in vesicles in the axon terminals. So at rest, the resting membrane potential of the neuron is negative 70 millivolts. So what happens to stimulate the neuron is we have some sort of stimulus. In this example, I have drawn in a chemically gated channel. So what's going to happen is a ligand is going to bind this chemically gated channel, and that's going to cause opening of this channel, and that's going to allow, in this instance, sodium to flow into the axon, into the cell body, sorry. When sodium flows in, remember sodium is positive, that's going to bring more positive charges into the cell body. That is going to cause this membrane potential of the neuron to become more positive. That's called depolarization. So depolarizing the membrane, and when we have a channel open on the dendrites or the cell body, and we cause this change in membrane potential, this is called a graded potential. Remember, with a graded potential, the further we get from the stimulus, the less an effect that it's going to have on the membrane potential. So say here, we brought the membrane potential up to negative 50. As we move further and further away, our effect is going to be less. So it might be negative 50 here, then negative 55, then negative 60, then negative 70. So as we move away with a graded potential, that effect is going to decrease. So if this depolarization is great enough that this graded potential brings the membrane to threshold, which in most instances is negative 55 millivolts, at the trigger zone, if we get that depolarization to threshold at the trigger zone, then that starts an action potential. And that action potential, because this is an excitable membrane, is going to travel all the way down the length of the axon to the axon terminals. So the first thing that's going to happen, we have voltage-gated sodium channels are going to open as a result of that action potential. Sodium is going to flow into the membrane. Those gates are going to close. Then potassium, voltage-gated potassium channels are going to open. Potassium is going to flow out. Remember, our little mnemonic Nike, sodium in, potassium exits. Those gates are going to close. And then this is going to continue all the way down the length of the axon. Sodium's going to flow in, potassium out, sodium in, potassium out, on and on until we get to the axon terminal. When we get to the axon terminal, that action potential, that depolarization of the membrane is going to trigger opening of these voltage-gated calcium channels. Calcium is then going to flow into the axon terminals, and that's going to trigger exocytosis of acetylcholine. So this acetylcholine is going to get spit out into the synaptic cleft. Okay? As a result of calcium flowing into the axon terminals. Acetylcholine is then going to come in here and bind to the receptors on our sarcolemma. The sarcolemma is the plasma membrane of the muscle cell. These are chemically gated channels. So when that chemical, acetylcholine, binds the receptor, it's going to open these channels, and then sodium is going to flow in. We have sodium here, it's going to flow in. Sodium flowing in, once again, is going to depolarize the membrane, and this is an excitable membrane in our muscle fiber, so that's going to generate an action potential. That action potential is going to travel across the sarcolemma, then down the T-tubules, which are adjacent to the sarcoplasmic reticulum. This action potential is then going to trigger calcium to be released from the sarcoplasmic reticulum into the sarcoplasm, into the cytoplasm in the muscle fiber. Calcium can then bind the troponin. So calcium is going to bind these troponin, and that is going to actually, that binding is going to shift this whole troponin tropomyosin complex, so it's no longer on the active sites on actin. So once that troponin binds the tropomyosin, it pulls the tropomyosin off these active sites and exposes them. Once those active sites are exposed, our myosin can then bind. So the myosin heads are going to bind to these active sites on actin. And then the actin and myosin are going to slide past each other, and that is going to be how we get a contraction of the muscle. When our muscle contraction is complete, when we don't want to contract that muscle anymore, we actually have specialized pumps in the sarcoplasmic reticulum that are going to pump that calcium back into the sarcoplasmic reticulum for storage. Those pumps do require ATP, so we do need energy in order to return that, to remove that calcium from the troponin and return it to the sarcoplasmic reticulum. We also need ATP to break this cross bridge between actin and myosin and allow the muscle to contract. So we do need ATP to contract the muscle, but also to stop contraction. Up in our neuron, remember our sodium and potassium, sodium is moving in, potassium is moving out, which is changing that membrane potential. We do need to restore that membrane potential to resting membrane potential for future action potentials to travel down the axon, and that requires that sodium-potassium pump. We need ATP to run that pump. And remember, the sodium-potassium pump is reversing this Nike. So the sodium-potassium pump is bringing sodium out. We take 3 sodium out, and we're putting 2 potassium in when we're using that sodium-potassium pump. And that is to restore resting membrane potential to get back to that negative 70 millivolts. All right, a few more little notes. I've actually erased our muscle fiber and drawn in a second neuron here. Forgive my poor art abilities, but I wanted to mention a few other things as we're talking about this. So we said sodium is going to flow in, potassium is going to flow out, and that is going to continue all the way down the axon. That's how our action potential gets carried all the way down the axon. If this axon is myelinated, so if we have myelin sheaves on this axon, then this action potential can jump from node to node, which makes it faster because it doesn't have to cover as much of the membrane. So we can just jump from little node to node. That is called saltatory propagation. If we do not have this myelin sheath and the action potential has to travel the entire length of the membrane, it's slower, and that is called continuous propagation. Now, when we look at, when we're looking more closely at membrane potentials, say this first neuron is transmitting a signal to this neuron below. It's sending some neurotransmitter out that's going to bind this chemically gated channel. The channel is going to open and something's going to happen. Either sodium could flow in, potassium could flow out, for example. So if what happens when this ligand binds is that sodium flows in, thereby bringing more positive charges in, thereby depolarizing the membrane, bringing it closer to threshold, that's called an excitatory postsynaptic potential. Excitatory because we're getting closer to exciting this neuron, getting closer to initiating an action potential because we're getting closer to threshold by becoming less negative. So we're moving away from -70 towards -55, towards that threshold. If, on the other hand, the ligand if this ligand resulted in, say, potassium channels opening and potassium exiting, then that would actually hyperpolarize our membrane because the positive charges are leaving. We're going to get a more negative potential. Say we could move from -70 to -80 or -90. That is called an inhibitory postsynaptic potential because we're moving away from that threshold that needs to be reached for an action potential to be generated. So we're inhibiting that action potential from being generated. So that's called an inhibitory postsynaptic potential. If we have our second neuron, our postsynaptic neuron, gets an inhibitory postsynaptic potential, then that neuron can be said to be inhibited, which means it's going to be harder, it's going to require greater stimulus to bring that membrane to threshold to generate an action potential. If, however, we had that excitatory postsynaptic potential, say sodium is flowing in, we're causing a depolarization, we're getting closer to threshold, then this postsynaptic neuron is said to be facilitated. And that means it's going to require less of a stimulus to bring it to threshold because we're already partially there. So we don't need as large of a stimulus to bring the membrane to threshold to generate an action potential.